Okay, I hit the start recording.
Okay. We'll start the broadcast then.
The broadcast is now starting. All attendees are in listen-only mode.
I need to show my screen.
Yeah.
All right, there we go.
And you're going.
Okay, well, good morning to all of you in attendance. This is Mark Richardson speaking from Vibrant Technology. I'm actually in Colorado this morning, in Denver, and with me is Brian Schwartz on this broadcast, and he is at our home office in California. So today we are going to cover some more curve fitting topics, and I'm going to show you some examples of more advanced curve fitting in using Emiscope various curve fitting methods. So I want to show you, hopefully we'll get through 3 different projects today. I'm going to go rather quickly, but 2 of the projects you have in your distribution under application notes, so you can go back and review what I've done with your own software on your own system, if in fact you own Emiscope. And then we're going to look at one more project, hopefully before the hour is completed, and it's a case where we've got 3 different references, and so we'll get to that one after I show you some simpler cases. I'm going to start with an application note, and I now have opened up my my tab in Emiscope that says Application Notes, and these projects are some of the projects in our Emiscope application series that you can also download from the internet now. Our new website has made all those available to anyone. I'm going to go over here to this one here, which is called, well, let me see, it's not showing. It's actually application note. Let me just open it and we can take a look at it here. It's App Note 15, and it says multi-reference curve fitting closely coupled modes. So this example is going to show a case where we have 2 closely coupled modes. Now, by closely coupled, we mean that there's only one peak in our FRF data, and yet there are 2 modes there. So how do we know that? And we're going to discover, not only through the animation, but through curve fitting, that in fact there are 2 modes on this this simple PVC plate. But if we simply do an ODS animation of the data, in other words, put the cursor on a peak in the data and look at the ODS, or the deflection shape, we see something that we don't recognize as a mode. So let me go ahead and open this project here. Well, we're already open. So this is the project panel that's showing that we have a structure model in here, an STR file. We have a couple of data blocks, and you can see one is selected, and a number of shape tables, and then down below we even have some added files. Now, added files can be movies that I've made as part of this project, or they could be some camera shots that I've taken out on site when I've done this test, this modal test. So added files can be a number of different things. They can be doc files, Word files, Excel files, and so forth. But let's just go ahead and look at this this data here. Well, I'm going to open up the model, so I'll double click on it. There it is. Now I'm going to share this screen with the structure model and the data block, which has the measurements in it. So when I move this is my active window, and now if I press this button up here that says Arrange Windows for Animation, the 2 windows that I have open, the structure model on the left and the data block on the right, are what we are looking at. Now you see we have these little splitter bars that separate the spreadsheets, the property spreadsheets, from the graphics. The data shown on the left is graphics. So if I pull this splitter bar over, you can see that, first of all, at the top it says I've got 70 FRFs. So that is a typical set of measurements that are made on any structure. In this case, we used an impact hammer, and an FRF is always between 2 DOFs. You can see the DOFs here in the spreadsheet column under DOFs, and there's one DOF and then a colon and a second DOF. Let me just make that a little bit larger. I'm going to hold down the control key, place my mouse on the spreadsheet, hold down the control key, and expand the display so you can read it a little better. Okay, if I scroll through these DOFs, you can see that the first one is what we call the roving DOF. The second one is the reference DOF. Now, it doesn't matter how the data was taken. The roving is always the sensor or transducer that moves around on the structure. The reference is always the sensor that doesn't move during a test. Now, in this case, we've got roving is the first one, and then the colon, and the reference is always the second DOF. Now, this, as I said, was a roving impact test. So in this case, the roving DOF are all the different points where we impacted the structure, and the reference here is 0.7 in the Z. So if I go over here to my model and turn on my point labels, I can see where 0.7 is. 0.7 there is in the back. Over here we had an accelerometer mounted there to collect the response as we impacted the structure. Now, how do I know that? Well, if I look at the units here of the data, the response is in meters per second squared and divided by newtons, which is the force of the impact. So we measured both the force with the hammer when it was impacted and the response with an accelerometer, and we got acceleration in meters per second squared. So as I scroll down here to the bottom, you can see now after 35 of the measurements, this first column here are the measurement numbers. After measurement 35, the reference changes to number 35Z. So that's this other point over here on the other corner. So this test was done with 2 accelerometers, one mounted on each corner, and then a roving impact hammer to excite the structure at each of the 35 points in the Z direction. Now, Z in this case is the actual Z as defined at each of the points. So those are what we call measurement coordinates, and each point has its own measurement axes or coordinates, not necessarily the XYZ down here in the lower right corner of the graphics. Those are called global. Anyway, let's go ahead and start the animation here. And when I start it, I can start it from either window. I can come over here in the data block window and say Animate, Animate Shapes. And now it puts up a warning here, and it says the following source has multiple reference DOFs. So it has, the animation will only animate from one reference at a time, because mode shapes are only defined for one reference at a time, and they're independent of the reference. So if I want to look for mode shapes by animating my DOFs directly from the data and then put the cursor on a peak, that indicating that this particular peak is being dominated by a mode. That's what I'm looking for when I animate this data. I want to select a reference, and then I can animate from that reference and then go and select a different reference and animate from that one. So here it is. It's animating now. And I'm going to turn off some things here so that we can see a little more clearly. Now it's animating data from the cursor location. So you can see that as I move the cursor, let's go way down here to a peak down there. There is my data down there at about 23 hertz. That, with the exception of the one over there in the corner, that's a pretty good measure of what we would call a rigid body mode. And that's simply the structure itself bouncing on its soft suspension. Now, it could have been done with a rubber pad under it, or it could have been done with bungee cords hanging it from a frame. A number of different ways to excite a structure like this if we just want to look at its flexible body modes. But that's a good indication down there when I get a set of data like this that I've got pretty good results here, with maybe the exception of one corner. Let me change over and animate from the other reference. So I'll select the other reference. Now you can see I've got a different looking ODS, but I still have rigid body motion. So that's what I expect to see. Let me stop the animation because I know it's very slow. And we'll just crank this up to there. I'm looking at it in a quad view, so you can see that it's not flexing. That's not a flexible mode. That's what we would call a rigid body mode. The structure is just bouncing on some soft suspension. So that's always a good place to look at your data before you do any curve fitting, to see, in fact, if you have a consistent set of data. This is a lot of data, 70 measurements here, and as I animate from one reference versus the other, I can see that I've got a consistent set of FRFs. Now I want to drag the cursor out here and put it on this first peak that I find in the data. And you can see what the shape looks like. And then I'm going to shift it over to a different reference, and the shape is changing. Now that's an indication right there that that is not a mode. There's not a mode there exciting that's dominating that particular ODS at that frequency. Well, let me show you what a mode looks like. I'm going to go over to this peak here, and now you can see what looks like a bending mode. That looks like a bending mode, and now I'll shift over and animate from the other reference, and the shape didn't change. Let me do that again. I'll shift back to reference 35Z. There's what the deflection shape looks like from 35Z, and here's what the deflection looks like from 7Z. It didn't change. That's an indication of a mode of vibration. It doesn't matter which reference I use. I should get the same answer if, in fact, I'm looking at a mode of vibration dominating the ODS. Now, I just drug it over to a more complicated picture. The blue lines are a rough indication of node lines. So you can see the node lines are where there's no motion of the structure. And again, if it's a mode of vibration, those node lines should stay in the same place. And as it animates or as I shift to a different reference. So now you can see I'm selecting the 7Z reference. Now I'm animating from the 35Z reference, and the shape didn't change. That's an indication that at that frequency, the ODS is being dominated by a mode of vibration. That one is a more complicated twisting. I would call it a torsion mode, but we can always identify every mode by its frequency, what we call its natural frequency. That frequency will not change and the shape will not change unless some physical property of the structure changes or the material properties change. So either the boundary conditions, the physical shape, or the material properties have to change. Otherwise, a resonance or a mode of vibration will not change. Now when we look at this data, we're looking at ODS data. The ODS will change. We saw that. If I go back here to this, that ODS, that doesn't really look like a mode shape to me. And then if I shift to the other reference, it changes to something that looks totally different. What I would expect to see on a structure like this, a simple structure, is first bending, what I would call first bending, a very simple bending from along the long length, the weak length of the structure, or a torsion mode where it's twisting. And I don't see that here. So that's an indication just from the animation alone that we have got some closely coupled modes here. So that's our first clue that we need a multiple reference curve fitter in order to find these mode shapes. So let's go in now and do the curve fitting. I'm going to go under Modal Parameters and open up my curve fitting window. This is the data block with my measurements up above. There's my measurements, my FRFs, all 70 of them. And below is the mode indicator that will show me the peaks of this in this data as an indication of a resonance. Now I've got some of these traces selected here, the second from 36 on, because I was animating from them. I want to make sure that I don't have anything selected. Now if I try to curve fit, let's just go here and let's just do the first step of the curve fit. It says you have traces selected. Now I can curve fit selected traces. I may want to do that if I have some traces that I particularly like. They're noise free, the peaks are large. Those are going to curve fit better than where I'm near a noisy part on the structure, or I've got a lot of noise and not much motion. So maybe I don't want to curve fit that data. I may want to select. But in this case, let's use all of the data. So it says, do you want to unselect? And I'll say yes. Now it's going to build a mode indicator for me. And since this is acceleration divided by force data, I want to use the imaginary peaks because those are the strongest, or let's say the sharpest peaks. Now you can see I've got two resonance curves here. I've got one that's a blue line, and I've got one that's kind of an orange line. And I've counted the peaks. You can see I got two peaks down here at a low frequency. Those are my rigid body modes. I'm not really interested in those. I've got two peaks here, right here around where I had the cursor, and what this indicator is telling me is that there's actually two modes there because there's two peaks. Let me zoom in a little bit and we'll see that there's two peaks there. Two different indicator curves because I have two references, and there's also two peaks. There is another visual indication that I've got two modes. And now as I scroll over and look at these other peaks, there's only one there. And if I scroll further, there's only one. So those are indicating that there's not a repeated root, or what we call, in this case, a closely coupled mode. Now we'll look at a repeated root in a second. I use that term, and that actually has a slightly different meaning. In this case, we've got closely coupled modes back here at these two values of frequency that are very close to one another, around 100 and what is that, 190 hertz. So let's go with the second step now. I'm going to go back and we'll look at all the data. I'm going to go with the second step of curve fitting, and you can see that it's going to do a multi-reference polynomial. So the fitters, first it said multi-reference CMIF, that's a mode indicator, multi-reference polynomial. It recognized that I've got multiple reference data here. So it selected the appropriate curve fitter for me to curve fit this data. So I'm going to go ahead and say, give me the frequency and damping. That's the first step of curve fitting. And it found two modes down here at 23 hertz. Those are the rigid bodies. It found a mode at 187, 189, Let me make this a little larger so you can see the frequencies a little better. So there they are. There's two closely coupled modes. They're only a couple of hertz apart, less than 2 hertz apart. And then it found some other modes that are clearly isolated modes. And then it's drawn up the vertical lines here on my screen so I can see where those frequencies lie. Now before I go on, I may want to just remove the two rigid bodies, or we can leave them in there and go ahead and let the curve fitter fit those rigid body modes. And so we're going to go to the last step. We'll skip over stability. We could use a stability diagram. Now in our last session we saw that stability is good when we can't count the peaks. In this case we were able to count the peaks because we've got two indicator functions, and the peak counter actually counted the peaks on both indicators. I'm going to go ahead and do the residues now over here under residues, and I will simply press the residues button, and now it's got all of my modal data, and it's got it's drawn up a fit function on top of my log magnitude. I can look at the phase also if I go to the Bodie plot. So there's my phase and the log magnitude. And you can see that the curve fitter's done a good job of matching up my data. Remember, the fit function is just a necessary condition. It's not sufficient. The curve fitter, what's really sufficient is that we have some good mode shapes. And we saw from the ODS that those two closely coupled modes at 187 and 189, now I can animate those mode shapes right now to see whether the curve fitter in fact found some reasonable mode shapes. So let me put the animation back so we're sharing the screen between the curve fitter and the animation. And right now I can go ahead and start the animation and look at mode shapes. All right, it's telling me I've got multiple reference data again, and there it is, and it's animating the first rigid body mode that the curve fitter found. I'm going to turn the animation back on here, and there's what the curve fitter found. Well, it's similar to the ODS that we were looking at, not as clean, but that's not really what we're interested in. Those are the curve fit rigid body modes from the data. There is the mode we really were looking for. There's what the curve fitter found by curve fitting this multiple reference data, and that's what we expected. If you test any structure, and I don't care what it is, an airplane wing, a car body, a machine tool base, washing machine, whatever it is, you should see a simple bending mode like this at the low frequency in your data, at a low frequency. And we call this first bending. And then if I go to the next mode, the other closely coupled mode, there is what I would call first torsion. So those two modes were in the data. They should be. Every structure has these two modes, but they were so closely coupled that if I didn't use a multiple reference curve fitter, I could not find them. Single reference curve fitter would not find those two closely coupled modes. So that's what we wanted to see from the results, and we could save these results into a shape table and animate them from there, but we could not see these results by simply animating from the data block. We had to use a curve fitter to identify the mode shapes. There's that bending mode that we saw from the ODS, and of course the curve fitter recovered it also. And if I switch to the other reference, I still get the same mode. Let me go back to the two closely coupled modes. Okay, there is the bending mode from reference 35. if I go and animate from reference 7Z, I get the same mode shape. So there again is a validation that that is in fact a true mode shape because it's the same shape no matter which reference of data I animate from. So the Kwik-Fit data is matching up with my FRF data one for one, and even when I save this into a shape table, I'm going to have a multiple reference set of shapes in the shape table, and I'll have to pick a reference in order to animate one versus the other. Okay, well, let's go on and look at another case here, a more severe case, although we're going to use some very clean data to illustrate what we mean by a repeated root. A repeated root, and I'm going to open up application note number 14, and you can see I have a little flag up here that says app note 14 is multi-reference curve fitting repeated roots. So I want to double click on that one. It says, do you want to save this project? I'm going to say no. I can always come back and curve fit the data again. But now I'm going to open up a very simple structure here. Let me just turn off the there we go. So there it is. This is a simple structure. It's a circular disk, and let's just go ahead and animate some of its shapes. So if I come over here to the shape table, this is FEA data. So we actually built a finite element model of this circular disk. Very easy to do in Emiscope. And so now I'm looking at some of its shapes. So there's a shape at 108 hertz. I'm going to zoom this up a little bit here so we can see. And then below it is another shape at 108 hertz. Let me put the node lines on. It's a little easier to see the difference between these shapes. Now this is FEA data, so it's ideal. We didn't actually test this structure. We're just going to use the FEA shape data. And now I'm going to go to this second shape, and you can see that the node lines move. So those are different modes. There's two different modes, identical frequency. The damping now, you can see the damping is the same. Now with FEA modes, we don't typically measure any damping, but you can see that we just went in here and assigned a damping value of 1% to all the modes. So they all have a damping of 1%, which translates into a different damping value in hertz, but they all have 1% damping. And this is what we got out of the FEA solver. Now let me go to the next pair of, well, the next mode here is at 201 hertz, and there isn't another mode at 201. So that's that's not a repeated root. That's maybe what we would call an oil can mode. That's just a mode of this disk, and any structure like this that's circular and flat like this simple structure is going to have a mode like this. Now we'll go to the next frequency, and again you can see a repeated root here because there's two modes at 282 hertz. And if I click on the next one, you can see the only difference between these is that they have a different mode shape. So they have a different mode shape because the node lines have moved, but in fact the same frequency. Now let's go do some curve fitting on this data as if we had actually tested it, which we didn't, but I'm going to put these FRFs up here, and what we did is we took the analytical mode shapes, the FEA mode shapes, and we added damping, and then we went into the shape table and we synthesized some FRFs. So here they are. Let me just show you the command that we used to do that, but we won't do it right now. We'll do it, we'll just go ahead and use the data. So under Tools, synthesize FRFs right here. That command there is the one that we use to synthesize the FRFs from the mode shapes. Let's go back now to the FRFs, and you can see that we've got 480 FRFs. We've got 3 references here, 5Z, 15Z, 25Z. How do I know that? Well, let's go look at how the data was labeled once it was synthesized. See, the first bunch of measurements there is 5Z, and as I scroll down here, now it switches to 15Z. So right here I've got 160 FRFs with 5Z. Now it starts over again, 161, and I start over at 1Z and go all the way down here to 25. So again, there's another reference here starting right here. So at measurement 320 is the last one with 15Z, and now we switch over to measurement 321 is reference 25Z. And you can see this is acceleration divided by force. Now we're back to imperial units, inches per second squared, and pounds of force. Let's take a quick look at where those 3 references are on this model. I'll click here and I'll turn on the point labels. Okay, there they are. Let me stop the animation so we can see. Okay, so I'm going to make this a little larger so we can see where 5Z, you can see 5Z for this particular mode is close to a node line. 25Z or 20.25 is going to be right there in the middle. That'll be a good reference for looking for some of the modes. And then let's see, we had 5Z, 15Z is over here. So these are our 3 references. 5, 15, 25. Now remember, the reference doesn't really matter. We could pick any point on this model and any direction as a reference and put our accelerometer on there and do an impact test. That would be the easiest way to test this, just like we did the previous PVC plate. But here it's all just simulated. We chose 3 references. We synthesized 460 or 80, sorry, FRFs to simulate a multiple reference impact test where the accelerometers would be located at 5, 15, 25Z. Let's go ahead and look at this data. I'll stop the animation here for a minute. Well, let's do this. I'll stop it from here. Let's start the animation from, I'm going to put this shape table down because we're not going to use it. And let's just do an ODS animation from these measurements. So animate shapes. It says select a reference. See, it's already looked at the references. It says you've got 3 references in this data. Well, it's just saying multiple references. The data block's actually named 5Z, 15Z, 25Z. Okay, so there is the animation. And let me just let it animate here a little bit so we can see how it animates. And then I'm going to move the cursor over here to the first peak. Now we've already looked at that mode shape. I'll turn the point labels off just so it's a little easier to see. And we can see, and let me zoom in here a little bit so we can get this cursor right on the peak. Well, the animation stopped, so let me start it again. So there it is. There's what the ODS looks like from Uh-oh, I lost my, I'm going to have to get my selection box back. So select traces, select by, and I'm going to pick in here reference DOF. So there it is. This is a selection box where I'm animating from 5Z. Now let me animate from 15Z, and you can see that the ODS changed. So there is a problem right there. That's not a mode, because we already know that there's two modes there. So depending on the reference that I animate from, the ODS changes. There's my indication that this is not, the ODS is not being dominated by a single mode. There's actually more than one mode there. Well, we already know that because we know what the answer is. Now here's the oil can mode. Pretty clean there from our data. I don't quite have it right on the peak. There's the oil can mode, ODS. Now let me switch to a different reference. And it didn't change. The shape is the same. And if I go down to the third reference, it didn't change. So there's an indication of a mode or a resonance, one resonance dominating the ODS. So let's close this and go in and see if we can get the curve fitter to sort these modes out for us. Here we are in curve fitting. I'm going to undo that. Let's go back to a log magnitude. And here's my data. So here's my 400 measurements. You can see I've already got some indicator functions down here. Let's just clear out everything. Right up here on my toolbar, here's the curve fitting toolbar. The first button there is clear all data. So this is going to clean the slate so that we can start the curve fitting over again. So let me go and compute the mode indicator. It says multi-reference CMIF. I'm going to go ahead and do that. It says you've got measurements selected. You want to unselect them. I'm going to say yes. We'll look at the imaginary peaks. And here's what this indicator looks like. Now again, we need to kind of zoom in here. You can see it's counted 19 peaks. Okay, and let me just zoom a little bit, and basically it's saying you've got 19 modes in here because these mode indicators, there's actually 2 of them that are visible. There's really 3 of them because I've got 3 references. The third indicator is not showing up because there's really only 2 modes at each of these various frequencies. We saw that from the data. And right here is the oil can mode, just 1 peak showing that it exists. And then over here are 2 peaks. And as I scroll along here, all of these other indicator peaks are showing me that there's actually 2 modes. 2 modes, 2 modes, all the way across the band. And so the curve fitter now knows that in fact there are 19 modes here. So if I zoom out, and I'm counting all those peaks, there's 19 modes. Now, you saw we went through the frequency and damping, and then we also went through residues. Kwik-Fit is a quicker way to do it. Kwik-Fit will use the methods for frequency and damping, the method chosen for residues. You can see it's multi-reference polynomial, and over here is multi-reference polynomial. And we've already done the indicator, so it doesn't need to compute a new indicator. Kwik-Fit is going to just go ahead and do the whole job for us by executing 1 button here. And when it's done, there it synthesized the FRF. Now remember, this was ideal data. It was synthesized from the mode shapes themselves with the 1% critical damping. That's a little artificial, but we needed that in order to synthesize an FRF. And you can see the Kwik-Fitter has found the modal properties of 19 modes And you can see their damping percent is all pretty close to 1%. So this is kind of a round trip here. It's gone through, it's found all the modes, their frequencies, their damping, their residues, and now I can go ahead and animate these mode shapes as they are. Let me again click on the structure model to preserve its size and then arrange for animation. And now I can start the animation right here. I'm going to click on this window. Now my toolbar shows animation. And again, I get the same message. It's a multiple reference set. And now I'm animating over here. Now you can see there's some points selected. That's why some of the points are a little larger, and the selected ones where we had the labels showing up before. So let me just pull this down here. So there I am animating a mode. Which one? Let me go up here and see which mode I'm actually, okay, so it's showing me the first mode is being animated. I'll push this box up here a little bit so I can see it. Now I'm going to look at that mode, and now I'll shift to the second reference. Mode shape didn't change. I'm going to shift to the third reference. It didn't change. The picture changed momentarily, but it's displaying that same mode shape from each reference. That's my indication that I have a true mode shape. Now I'm going to click over. There's the other mode at 108 Hertz. Again, I can click through its references, and the picture does not change. There's a clear indication that from this multiple reference set of data, we have indeed found the mode shape correctly. The curve fitter has. There's dual can mode, and again, if I click through, I can see it doesn't change. It doesn't matter which reference I animate from, I get the same mode. So this is another clear indication of the rule that I've been telling you. The reference doesn't matter. And when you're taking data on a real structure, you want to pick a reference where the peaks are large, so the curve fitter will do a better job. And you can be unlucky and pick a reference that's right on a node line, but in a practical sense, in the real world, it's very difficult to put your accelerometer right on a reference and not see the peak at all. But you want to pick a reference where you think the peaks are going to be large. But since you don't know what the mode shapes look like, you just have to take a guess. Now, if you have an FEA model, that's very useful for giving you a quick look at the mode shape. So again, you can pick a reference so that you're not sitting on a node line of a particular mode. But you can see that these modes, here's a mode here that's very close to a node line for reference 5Z, but the curve fitter is still finding that mode because I'm not quite on the node line with the 5Z reference. So it's still doing a good job of finding that mode from the data. Now again, this is ideal data. If I had noise, may not be successful with the curve fitting from reference 5Z from that data. Because remember, 5Z, let me put the labels back on. 5 is pretty close to a node line. With our references were 5Z, 15Z, and 25Z. So we did pretty good in picking those references. And here's another mode. We haven't looked at this mode yet. It's another repeated root. Same frequency, different mode shape. No problem there. Those are good references. There's 15Z right smack on the node line of this mode. So let's just go look at reference 15Z. Well, there's the mode shape. So the curve fitter with nice clean data like this, even when we're sitting right on a node line, is doing a pretty good job of curve fitting that data. Now the peaks are going to be very small for reference 15Z, but since it's ideal data, the curve fitters can still find that mode shape. All right, we got some time left here. Let's go on to the third example that I want to show you, and this is some data that we received from one of our, I'm going to close this, one of our Emiscope users, happens to be a reseller that makes a living using Emiscope, doing modal tests, also doing a lot of acoustic testing because of structure-borne noise problems, very common in industry. And so many times if there's a noisy machine or an objectionable noise, it's because a resonance is being excited somewhere in a machine or in a structure, in a piping system. Depends on what it is. We call that structure-borne noise. So resonances are audible many times, and then many times they're not. But the machine may just wear out too quickly or break, castings break, and weldments come apart because of too much noise. I mean, too much vibration. Down here in this project, I've got some pictures of this test article. Now, this is a grating. Let me open up one of these and show it to you. There it is. It's a grating in a water treatment plant. And apparently, the customer was having some issues with it. So Navcon Engineering, who uses Emiscope to do their consulting work, was hired to come in and test this thing to do a modal test and show them what the modes of this thing look like. So perhaps they could come up with a solution to prevent it from failing so often. Let me just show you a couple more. Okay, so here's showing an impact test. Now this is a multiple reference test. We'll look at the data in a minute, but a lot of data was taken on this grating by impacting in the X and then the Y and then the Z at a fixed point. And you can see the point here is on the corner. This is a rather large structure, so a large impact hammer was used with a load cell on the tip to measure the force, and it was impacted in the X, the Y, and the Z. So again, multiple reference set of data where now the force is the reference as opposed to the accelerometer being the reference. Here's a third picture. So here's the second reference where now it's going to be impacted in the vertical direction at the same point. So that, since the point is the same, and the whole impact test will be done by hitting in the vertical and having accelerometers placed all over the grating. And there is the third impact in the horizontal, hitting it in a different direction from the first. And you can see some of the accelerometers out here on the grating measuring the response for each of these tests. So very valid impact test, multi-reference impact test. Here's another picture of the grating, and we'll see quite a few test points here. There it is again. So a lot of data taken on this to define its mode shapes over quite a frequency range also. Okay, well here's the data. Let's just take a quick look at the measurements. You can see this was from DC, 0 hertz, up to 250 hertz. So a large structure, quite a few resonance between DC and 250 hertz. So I've got some of them selected here. Let me unselect. Now you can see he did a good thing here. He colored the data from each reference with a different color. And that's a very good idea. I'm going to zoom in here a little bit so we can look at the references. Now his data is organized by reference 1, 2, and 3. 1x, 1y, minus 1z. Now he goes to the second point. Well, the second, yeah, see here we got a roving DOF of 1x. Now we have a roving DOF of minus 1y, but the same references, 1x, 1y, minus 1z. Now I can sort this data differently, and so I could have all the 1x reference first, all the 1y second, all the minus 1z third. It wouldn't matter, only my animation, I'd have to reconstruct my animation equations. We're not going to go into that today, but in order to animate this data, we need to go to, because the animation engine looks at the measurement numbers. And you can see these are all measured in sequence. And if I sorted them, so here's the lot of measurement 2. So in this case, he was defining the same point here, point 4 in the x as measurement 2. So his animation equations would animate whether he chose reference. It didn't matter whether he chose 1x, 1y, or 1z. The animation engine would pick up the appropriate data for measurement 2 here, and but then 1 would be selected, and that only that data would be animated. So you can see he set this up a little differently, where his multiple reference data, each case for the roving x, y, and z, it's the same point here, 26z, but different reference. So his animation would work correctly there because only one reference would be selected at a time. Well, let's go in and curve fit this data, and then we'll look at some of the mode shapes. And we're going to talk about something else that I've alluded to called modal participation. Now we've seen that in the ODS. If we animate from the ODS, we'll see the participation, but the curve fitter will also tell us the participation of the mode. So I'm going to go through here, and this is multiple reference data now. I want to go ahead and compute a multiple reference CMIF. Same thing we've been doing. And there it is. You can see there's just a lot of peaks here. Well, I'm going to kind of zoom in around the first few here, and we'll just focus our attention on a few of them because there's just so many resonances in this data we don't necessarily. So you can see some very clear, and since this is multiple reference, we don't see any closely coupled modes or repeated roots here. As I scroll across, we've got 3 indicators because of the 3 references, but we're pretty much seeing a single mode at each peak. Now it's counted a whole bunch of them here, 35. We're not going to go up here. This is just a lot of data that would take us some time to sort through that, but let me just show you. Let's just take the first 5 here. So I'm going to set up the band cursor because I want the curve fitter to just focus on those first 5 modes. And again, I'll use the Kwik-Fit. It's my favorite curve fitter. I could use stability. We could go back and use that, and for this type of data, stability would work just fine. It's lightly damped data, not closely coupled. Curve fitters will all work well on this type of data. So there it is. We have 720 FRF, 720 measurements with 3 references. So each reference has whatever that is, 720 divided by 3. And you can see I've got, let me show you the Bodie. I want to look typically after the curve fitter to look at the Bodie to see if both magnitude and phase are being matched up well. Now you can see there's a lot of phase wrap in this data. I'm not concerned with that. I am more concerned about whether the red line lies on my measurement data in the vicinity of each resonance peak. So here we have a particular measurement where I've only got really 2 strong peaks in the data, and so I'm very close to a node line for 3 of the modes. Only 2 of them are being defined well in this data. But as I scroll through here, you can see the curve fitter has done a very good job of matching this data. Not perfect, but this is real experimental data, and we've curve fit 5 of the modes. Now, the other thing we get out of a multi-reference curve fitter is something called modal participation. And this is used by the curve fitter itself. You can see it right here. I've drugged this column over. So normally this column would be way over here to the right. Let me put it right in here. So here's our frequency, our damping in percent. Maybe let's just look at 1 damping. Well, we'll leave them alone. What I wanted to show you here is the modal participation. And this tells us which reference the mode is best defined by. In other words, where are the strong peaks for a particular mode in a particular reference of data? So you can see here the modal participation. There's a participation number for each of my references. 1x, 1y, minus 1z. And for this particular mode at 16 Hertz, at first peak in the data, it looks like its participation is very strong in the vertical, the 1z, and hardly any participation in the x and the y. Now we go to the next mode here, and it looks like it's participating in the x and in the y, and not so much in the z. The third mode here is participating mainly in the y direction. So what that's saying is that its dominant motion is in the y direction. Even though I have data in the x, y, and z, before I took this data, and I didn't take it, but before it was acquired, and remember we impacted in the x, y, and the z, we had no idea what these mode shapes look like, but now the curve fitter is telling us that the mode shape for that third mode, the 31 Hertz, is going to participate in the y most of the time. In other words, when it animates, that's where the peaks are the largest, that's where the strong motion is. That's the dominant direction of that resonance. And we can go through here. The fourth one, the dominant direction is in the z. And then finally, the fifth mode is again back in the y. So let's go ahead and animate this data and see if in fact that's what these mode shapes look like. So I'm going to start the animation over here I'm clicking in this window, and I'm going to use the curve fit animation up here. So this says curve fit shapes, animate shapes. That's where I get the curve fitting started from. And what that means, it's going to animate directly from my curve fit data. I could save it into a shape table and animate there, but in this case I'm going to animate just as quickly as I've done the curve fit. So let me start this up. All right, same question. You've got multiple reference data. Which reference do you want to animate from? And it's chosen one for me. So there is the first mode. Now let's go back and look at this participation. I'm going to drag the participation column here. Just click and drag. We can do that with all the spreadsheets. You just click and drag on the header of the spreadsheet column, and you can reorder your spreadsheet column so that you can look at particular data. So there it is. In this mode, the participation is primarily in the z direction, and in fact that's what we see in the animated picture here. Z direction. Now if I go to the y and animate from there, I see the same mode shape because the curve fitter has found from that, the multi-reference is saying, hey, it doesn't matter what the reference is, I'm going to give you the same mode shape. And that comes out of the curve fitting. Now the y and the x may be data with no peaks in it, but the multi-reference curve fitter will take care of that when it uses these participation numbers down here to do the curve fitting. So I'm giving you a little bit of the behind the scenes, but probably not explaining it completely for you. Okay, the second mode here is participating mainly in the X and Y and less in the Z. And sure enough, you can see that. Let me just go to the quad view here. You can see that in the quad view, the Z motion is very minimal, but the X and Y is very well defined. So this is always true for any mode shape. We never know until we've done the modal tests what the dominant motion is. Let's go to the third one. There I have dominant motion in the Y. Now this is really telling me this is the reference, which in this case is the global Y direction. And so I can look at this little indicator down here in the corner. And again, if I click on the other two directions, let me go to the quad view here. You can see that in the X direction, there is hardly any motion. I'm looking at from the side or from the top. No motion. It's all in the Y direction. And the next mode now, we're back to the participation is in the Z direction, dominant in the Z, little bit in the Y, and very little in the X. And finally, the last mode, we're back to participation mainly in the Y. So this is where multiple reference testing just gives you more information. Could I have gotten these same modes from a single reference test? Perhaps I could have. But never having tested a structure like this, it's always better to take additional references of data. And then we saw today how the animating the ODS is going to indicate, that'll be our first indication that we've got closely coupled modes or repeated roots. And then in this case, we could see that even though we had no closely coupled modes and repeated roots, the mode participation is telling us the dominant direction of motion of each of the modes. I think that's our hour. It's done. Brian, do we have any questions that I could answer before we wrap up this session?
No, we haven't had any questions come in.
All right. Well, I apologize. I should have given you a heads up on that. You could have sent email questions to Brian Schwartz while the seminar was going on. We didn't have any questions today, but I want to thank you all for coming and hanging in there for another hour of Emmy-Scope training. We do this every month, so we'll be back here next month and we'll take a different topic and explain some more of the details of using Emmy-Scope to get your job done. So thanks a lot. Have a good day and talk to you soon. Bye.